good afternoon, good evening, and good night. My name is Jeremy Anthony Gunawan from the class Fluid Mechanics 3. Today I'm going to tell you about the first assignment that Mr. Dai um, gave us. So let's just start right away. For the first assignment, Mr. Dai gave us this um, project for us to solve, uh, which is a gate valve, and we are told to study the flow through a large shack with 2 feet diameter inlet and carrying a water at a flow rate of 30 CFS. We have to complete the model and the prototype given the data here, like the debit and stuff. So we have to find the required flow rate in the model. So Mr. Dai also told us to find the connection between a Reynolds number and the pressure drop. So using the software CFD I imported the geometry file, which was used in another class, which is numerical method. Now, after importing the file, I used uniform scaling um, to set the dimensions for the gate valve to make sure that it's correct and same as in the problem. Now this is the dimension that we got. We can count this to count the exact diameter of the inlet to make sure it's the same with the problem. After that, I put on maximum level 2 on the surface refinement, and I also added layer mesh number of layers 5, expansion ratio 1.25, and the first layer of thickness 0.2 on the layer mesh parameters. Also, don't forget to put the box mesh boundaries based on the geometry. X negative is inlet, X positive is outlet, Y positive is wall, and the others is just boundary. And then I'm going to pick a mesh location, which is located directly in the middle of the gate valve. This is the location that I got, the coordinates, and then before I generate the mesh, I checked if it was okay, and it says it's okay. Then I generated the mesh. This is what it looks like. So the next thing to do is set up a few conditions before we simulate the model. So the first thing is to change the turbulence to RANS or RANS, and then it'll pop up a new tab called turbulence, which will change the turbulence model into SST-K omega, and then we'll change the material to water because the fluid is water in the problem, and then we'll input some things on the boundary conditions like changing the phase name to inlet 1, and then putting in velocity inlet and putting 22.8 meters per second as the reference value velocity, and then put the outlet phase into outflow and the wall into stationary wall. We can get these velocity later on. I'll tell you how to count it. So this is how it was done. So we have the formula Q prototype equals D prototype divided by D model multiplied by Q model. So 3 over 12 feet divided by 2 feet times 30 CFS equals 3.75 CFS. So we'll change the Q model into the Q prototype, and then we can count the reference value velocity by dividing Q prototype with the area, which was pi divided by 4 times the diameter, which is 0.077, and then we shall get 22.8 meters per second. And then after that, we'll set the iterations and the interval into 2000, and then generate the mesh. After the mesh is completed, the simulation is completed, we'll change to another software called ParaView, and then we'll input some formulas like the static pressure. This is wrong. This is supposed to be the magnitude of the velocity, which was the square root of this velocity of x, y, and z vectors, and then we'll put in dynamic pressure with these formulas and the total pressure. So after inputting these formulas, we can get the inlet and outlet total from the simulation beforehand, which was this data. And then after getting the total pressure, we can get the Reynolds number, which we can count by the formula given here. Reynolds formula is equals to the fluid velocity times the pipe diameter times density divided by fluid dynamic viscosity. And then we can get the Reynolds number for the 22.8 meters per second speed, this number. So in 1,972,584.27. So that was 30 CFRs, right, from the Q model. And then we'll find a few just to make it more accurate. We'll change 25, 20, 11, 15, 10, 5, and then we can get these data here. So we'll change it to Q prototype, and then we'll find the reference value velocity, and then we can get the pressure drop and the Reynolds number. So after we're done doing this, we can get the graph here. I apologize, the graph should be going upwards, but the graph is right, but it's just going downwards. So there are two graphs. There are pressure drop and velocity graph and pressure drop and Reynolds number graph. So these two graphs show that the connection or the relationship between pressure drop and velocity is proportional and directly proportional. So the higher the pressure drop is, the higher the velocity, and the lower it is, then the lower the pressure drop is. Same with the pressure drop and Reynolds number. So the higher the Reynolds number is, that means the higher the pressure drop is, and vice versa. So that's it for the first assignment by Mr. Dai. Thank you for listening. Goodbye.